Przed Wami Marcel, który opowie nam o kolejnych podatnościach. Marcelu, proszę bardzo.
Hi, thank you. Okay, we had a very slight delay, but whose experience with operational technology, commissioning devices and so on, this is quite normal, and apologize for the misalignment of the text. I created it in PowerPoint, now it's running on OpenOffice. Anyway, let's move on from network-based attacks to hardware-based attacks. Okay, and who's ready for some hardware hacking? Okay, then the other ones can go for lunch. No, but seriously, connectivity is the backbone of Industry 4.0 applications. And little edge devices, often put into the electrical cabinet, facilitate the communication across networks, sometimes even worldwide. But what if I told you it only takes a few tools to compromise such a device? I'm Marcel Rick-Cen. During the daytime, I am an OT and IIoT security consultant. I am the product owner of our in-house OT remote access solution. And from my educational background, I have a master's degree in automation engineering and roughly 2 decades of field experience. In my nighttime, I'm a content creator and OT hacker, or if you want to put it a bit more formal, I'm an independent OT security researcher, and I look at what makes and breaks OT devices. This month, I also started my own platform, Rick-Cen, where I teach community-driven industrial cybersecurity courses. And today we are having a look at an OT remote access and IIoT edge device, something like this. This is put into the electrical cabinet by integrators or machine builders, and this facilitates remote access from the service technician over the cloud portal to the machine. This particular device also offers some data aggregation functions, so it also functions as data collection and IIoT edge device. And I looked very hard at this device and found a CVE, namely hard-coded root credentials, and this is what we're looking at today. And like I said, you don't need an expensive hardware hacking setup. Yeah. You only need round about 30 euros of tools. You need a digital multimeter, screwdrivers, prying tools, a USB UART interface, and a USB logic analyzer. And if you have that, it only takes 6 steps to gain root access to a device. And this is what we are going to do now. We are looking at the hardware, we're measuring the signals, access the console, break into the boot shell, dump data, clean up the data, and then enjoy root access. Let's start with the first step. First, when we open up a device, we look at the components. What's the system on chip? Where's the firmware stored? And are there any debug interfaces? And if we open up this device, we find a MediaTek system on chip. The firmware is stored on a WinBond flash memory firmware chip. And we find a debugging interface that, if you're familiar with hardware interfaces, who's familiar with hardware interfaces? This already screams UART in your face, right? You have GND, RX, TX, and honestly, this is easy mode in hardware hacking. In other devices, you have pins or pads scattered around the PCB, so this much more turns into a scavenger hunt. But great, now we identified our target. We are targeting the UART interface. We could directly connect our USB UART interface and start connecting, but let's follow best practices and first perform electrical reconnaissance. We measure what is the electric common ground, what are the voltage levels, and are any logic signals transmitted. So if we fire up our digital multimeter, the first step is to establish the electric common ground. We switch the multimeter to continuity mode, and we hear a beep if we connect the GND pin to the casing or to the GND of the power supply. Then we can power on the device and get voltage readings. On both pins, they are in the 3.2 volt area, and this is very good news because this is in the range of the 3.3 transistor logic voltage range. So now we can go to the next step and connect our signal analyzer. In the signal analyzer software, no, it doesn't look like this. Oh boy, this is a horrible signal. Okay, in the in the signal analyzer software, you see rectangular waves on the screen going on for quite some time, confirming that indeed we have logic signals going on X3, the transmission pin. Then also with the logic analyzer tools, we can determine, sorry. We can show this on the PDF. Yeah, we also have the PDF. Yeah, let's switch to the PDF. 1 second. Maybe this would be some logic signals paired with quantum computing, you know, because you cannot have a logic 0 and logic 1 and also something in between. But this would be next level hardware hacking. Okay, then we switch to the PDF. This takes a bit out of the suspension and tension I built in the presentation, but I mean, you probably can guess the end result anyway. I mean, it's in the title of the presentation, getting root access. Okay, great. Now we have less smooth transmissions, but our rectangular signals look good. So, and if we use the protocol analyzer in the logic analyzer software, it interprets the rectangular signals as ASCII text, and this looks like a bootloader output to us. So we can go on to the next step, serial console access. We connect our USB UART interface, read the boot log, and look for interesting system information. When we connect the USB UART interface, we must cross RX and TX, because in one device the transmission channel must end up on the receiving channel of the target device. We immediately learn that the system is running on the U-boot bootloader and is running on OpenWRT, a specialized Linux image for switches, routers, edge devices, and so on. And at the very end of the boot log, we are prompted for login, for which we don't know the credentials yet. If we scroll a bit further up, we see how the firmware is partitioned. It gets split into data for the bootloader, factory data, firmware data. Then the firmware data is split into 2 more partitions. And most hardware hackers or IoT hackers would go for the rootfs file system, right? Because that's where the goodies are. But not us, we are in OT, and in OT everything is different, so we go for the factory partition. If we scroll further up, we're also prompted for a spacebar press to enter the bootloader. But on this device, the timing window is so narrow that it's almost impossible to hit. Right? I was sitting like a maniac over the keyboard and slamming the spacebar, only to see that if I hit the timing window right, I'm presented with a second option to press number 4 to enter the command line interface. So let's get boot shell access next. We want to automate our key presses. Then when we're in, we enumerate the available commands and dump the factory partition. On the left side, you see a very simple bash script where I utilize XDO tool. This is a standard tool in Kali Linux to send key presses. And here I instructed to send a spacebar press, followed by number 4 press, sleep for 0.1 second, and then rinse and repeat. We start the script, start the device, and we hit the boot shell. Here you see in the top line the prompt of the boot shell, where some more space bars and 4s are spammed into the prompt, which the bootloader or the boot shell, of course, doesn't know what to do with that. And we moved on by enumerating the commands. Okay, who's familiar with the U-boot bootloader? This is already a very restricted command line, right? In the unrestricted U-boot shell, you have much more commands available. But interestingly, the manufacturer left memory access and memory manipulation commands in there. At this point, most hardware hackers would go for the environmental variables because there you can set so-called boot arguments, which are passed from the bootloader to the kernel. And if you put a snippet of code in there to spawn a root shell, this would work on IoT devices, cheap home routers, but not here. If you manipulate the boot arguments, the checksum fails and it falls back to the defaults. But down here you see the SPI command, and with the SPI command we can directly access the non-volatile flash memory, which is where the firmware is stored. And remember, we were going for the factory partition. So all we need to do now is to issue the SPI read command, specify the start address where the factory partition starts, and enter the length for the length of the factory partition, and we get a readout of the hexadecimal of the data in there represented in hexadecimal notation. Great, now we have our dump of the factory partition. Let's move on to data cleanup next, where we will format the data and converge the data. Because if you look closely, the bytes are misrepresented in hexadecimal notation. Up here you see some single hexadecimal digits, and each byte must be represented by 2 hexadecimal digits. Else you will have a misalignment of data, you will have a misinterpretation of data, which will lead most likely to garbage after conversion. Additionally, the data we see here is hexadecimal, but stored in text format, and we need this as binary data to move on. So we write a very simple bash script to go through the data, and every time it finds a single hex digit, it puts a 0 in front of it to ensure that everything is represented by 2 hexadecimal digits. Once this is done, we can use another onboard tool of Kali Linux, XXD, to convert the text hex data back into binary hexadecimal data. And once this is done, we can open the freshly created binary file with XXD and hex editor or strings on Kali Linux. And here, can you see that in the? Yeah. Then we see the ASCII interpretation of the binary data in there. So we are done with the data cleanup. All we need to do now is interpret the data and log in. But where do we start? Here we have seemingly 3 random chunks and strings of data, right? And this could mean anything, and our research is stuck at this point, right? Unless we put ourselves into the shoes of an automation engineer and a hacker who thinks, this somewhat looks familiar to me. Where did I see this before? And the data that is stored in the factory partition correlates with the data on the device label. So here we can match the serial number, we can match the device version, down here we can match the password for the web management login, which leaves us with 2 unknown strings. One is 30 and the other one seemingly random letters and numbers, right? And this unknown string didn't let me go because this was for the part where I wanted to build the tension. This has the same characteristics as the web login password. It has 10 characters, capital and lowercase letters, and numbers. And this just screams password in your face. So if we try to use this unknown string and assume this is the root password, we can log in as a root user on the device, getting unrestricted access or unrestricted console access. The device also runs an undocumented SSH server, so you also can log in with the root credentials to the SSH server. So, someone at this company must have looked at this and said, okay, we're putting the credentials in plain text in there, but this is fine, nobody will find it, right? Then I reached out to the manufacturer on a Sunday because I was already a bit in contact with the head of security. And he replied 2 hours later stating that this is very concerning and asking me to forward everything to their security email. And they will look at this the first thing Monday morning. Around Monday lunchtime, I had a reply, and I must say the conversation with them was very friendly and supportive. And they explained, yes, this factory data is put into the device during production, and each password is randomly generated. And therefore, they deemed this to be an acceptable risk. Especially, they stressed that all the machine builders should follow security best practices, locking this up in an electric cabinet, making physical access as hard as possible. Then I registered an CVE for that, and now I'm here to tell you about this digital or hardware and digital scavenger hunt. But what are the security implications for this? There might be a slight chance that you could have a backdoor device if you are a big enough target and happen to operate this device for your remote access or edge device functions. Right? I mean, a threat actor, APT or state-sponsored could intercept your shipment, open up the device, read the root credentials, backdoor the device, put it back into the packaging and forward it to you. If you're operating critical operations, be sure only to buy from trusted sellers. And if you deem this to be high risk or critical, demand a tamper detection and protection for that. So, but what is the takeaway of this? I want you to stay curious and look beyond the network. Because, of course, in industrial automation, OT, you name it, process automation, there has been a shift of mindset with cybersecurity. And from my gut feeling from 2010, 2015, of course, manufacturers established cybersecurity in their products, but they only secured the network layer or the network attack surface. Because this device was very hardened on the network level, but it didn't stop me on the hardware level. And of course, security doesn't stop at the Ethernet port or at the Wi-Fi antenna. So I want you to also look beyond the network, stay curious, and if you're interested, you can join my course, Industrial Embedded Systems Hardware Penetration Testing, where we will hack this device. Does anyone recognize this PCB? This is a globally available low-cost ESP8266, for which I wrote a custom firmware to mimic the behavior of industrial controllers, so the participants can get hands-on experience without breaking the bank. Because let's face it, if you go for a common hardware hacking course, you hack a cheap IoT device like a camera or internet-connected bird feeder or a $20 home router, and getting hands on a real industrial device is the barrier is much higher because you pay at least 500, 600 euros, and sometimes it's also not available to the public market. And I bypassed that with this device. And after the course, the participants can also flash another firmware on it, maybe a Wi-Fi deauthor, or get into home automation. Okay, that's the end of my talk, and the end slide is missing, where it basically says thank you, and I wanted to invite you to my website. It's rickcen.com/cybertech2025, where you also can download the research paper to this finding, where you can download the PowerPoint slides and a hardware hacking cheat sheet to get you started. Okay, it looks like we still have 1-2 minutes left. Are there any questions? Yeah.
Okay, moment.
There's the thank you slide, and there's the link.
Okay. One question. Have you confirmed that this password is unique per device? Do you have a chance to just compare with other devices?
Not yet, because I only have one of these devices at home, and actually the vendor sent me a second device. for some hardware glitching attacks, where you can also read about in the research paper. And from the device label, the web login password is different, so we can assume that the root password is hopefully also different.
Maybe, but I think that is a good vector to check it, because this is very typical response from the vendor with similar vulnerabilities.
Yeah, I mean, this leaves some bigger implications, because if you have access to the whole device, there are also private API keys and whatnot stored on there. But this is a topic for another security analysis.
Yeah, thank you very much.
Do we have any questions? Three, two, one. Thank you.
Okay, thank you. Have a good lunch break and enjoy CyberTech 2025.